Hello and welcome to our fourth lesson on high school algebra. My name is Joydeep Ghosh and I am a theoretical physicist. Mathematics has always been one of our most powerful tools to understand the real world. We use it to describe natural phenomena, to solve practical problems, and to make sense of complex systems. The world, however, around us isn't made up of isolated objects alone. It's full of interactions. Matter interacts with matter. Light interacts with matter. Economies and markets interact with each other. If math is to model the real world, it too must allow its objects to interact. That's where mathematical operations come in. We have already seen how numbers interact through arithmetic operations like addition, subtraction, multiplication, division. Now think a bit further. For set theory to become the universal mathematical framework, it must allow interaction among sets. And guess what? In fact, it does. That is exactly what we call set-theoretic operations, the focus of today's lesson. The two fundamental ways in which sets interact are union and intersection. Union shows how to combine sets, while intersection reveals how they overlap. Once you understand these ideas, you will see how they extend naturally to more advanced interactions among many sets. Let's dive in and explore.
Okay, so there are two set theoretic operations that exist, and the first one that we discussed today is called union of two sets. So let's say A is a set and B is another set. The union of these two sets is an operation denoted using this symbol and is defined as the set containing all the elements either in A or in B. Okay, so let me give a quick example. So let's say A is a set of single digit prime numbers, so 2, 3, 5, 7, and B is the set of single digit odd numbers, so 1, 3, 5, 7, and 9. Then A union B, the way we have defined here, means that I have to essentially collect all the elements from A and B and construct it. So 1, 2, 3, 5, 7, 9. So any element that go either way, either A or B, that will go here, right? Okay, so this is the union of two sets. Okay. Similarly, we have our second fundamental operation called intersection. Intersection, of course, intersection of two sets. So again, so if A is a set, intersection is denoted using this upside down union symbol, and B is another set, then A intersection B is defined as the set containing elements that exist both in A and in B. Okay, so again, based on the previous example, just to remind you that we said that A is the set of single digit prime numbers 2, 3, 5, 7, and B single digit odd numbers 1, 3, 5, 7, 9. Therefore, A intersection B, the way we have defined, is we have to collect the elements that are common between A and B, right? So 3, 5, and 7 would qualify for this. So A intersection B contains 3, 5, 7 because they actually go both in A and B. Good. So now let me draw a connection between the algebraic operation plus or addition and the union, the way we just defined. And what I'm going to do, I will actually draw a table here to explain it better. So in that world of arithmetic, probably you have seen everything that I'll discuss about the plus, and these are actually different laws that we talked when we discussed arithmetic. So let's draw the connection here. So arithmetic in the arithmetic world, we know that if we add two numbers a plus b, it doesn't matter which order we do. So a plus b equals to b plus a. Similarly, you can check in the set theoretic world, take just two examples of set and check that A union B, it is same as B union A. Oftentimes, this law is referred to as the commutative law. Commutative. Okay. Similarly, we have seen that um, it doesn't matter which order you apply plus. So for example, A plus B and then add C is same as A plus if you would have B plus C first. Okay. And in the set theory, what it means that A union B union C is same as A union B union C. Okay. This is referred to as associative law. Similarly, arithmetic, if you add 0 to any number, it doesn't add any value. And as we have seen that 0 is equivalent to the null set phi, therefore, if I do union between a null set and any other set, it won't change that set. So A union phi is A, often referred to as the law of identity. Okay, so these are actually the connections between the arithmetic operation plus and the union. Okay, now we draw a very similar connection between arithmetic operation times or and multiplication and intersection, the way we have defined in the set theory. And of course, I will write down the names of the laws here. Okay, so in the arithmetic world, if I multiply two number a times b, that gives me the same as b times a. So commutative law actually holds. Similarly, in set, you can check that a intersection b is same as b intersection a. We mentioned that this is our commutative law, right? Okay, so and also associative law holds for multiplication. So A times B times C, it's same as if you do A times and B times C first. Similarly, A intersection B and then intersection with C, same as A intersection B intersection C. So associative law also holds for both multiplication and intersection. Now, the third thing that is a little new, it actually combines two different operations together. So in arithmetics, we know that if I have A times and then B plus C within the parenthesis, then you have to distribute these times, right? So you can say A times B plus A times C. Similarly, in set, you can check that A intersection B union C is same as A intersection B union A intersection C. It distributes the same way as for times and plus in arithmetic, and it is referred to as distributive law. Okay, great. Okay, now I need to mention that there are some additional laws that we have to be aware of for set theory that is not easy to connect with arithmetic operations. So let's say A is a set, then therefore A union A is A, right? And that is same as A intersection A. So very intuitive, very obvious, but it is so important that it is often referred to as the idempotent law. Okay. And finally, let me remind you that if you have any set A and if you union it with respect to the null set, then you get the set back, which is A itself. And if you intersect it with the null set, then you get the null set, as we probably have seen. And similarly, if you have that set A and if you union with respect to U, here U is the universal set, then of course you get the universal set. And if you intersect with universal set U, then you get the set back, which is A. So these laws are often referred to as the laws for phi and the laws of U, and heavily used in proving many set theoretic theorems. Great. So finally, let me mention that there is another operation that exists. It's called the difference. Difference between sets. Difference between two sets, for example. And it is denoted as A minus B, where A and B are actually sets. Now, this is not at all obvious what we mean by difference, right, for sets, which are a collection of distinct objects. And this is not a fundamental operation. The way it is defined is the following. The definition of the difference between two sets says that A minus B is defined as A intersection B complement. Now, you must wonder at this point that what does it have to do with the way we know difference in arithmetic operations, right? So why we call it the difference between two sets? And it is not at all obvious at this point. And in order to make it obvious, what we need is we have to be able to we need a visual representation of sets. So we have to be able to visualize set and set theoretic operations. So this is exactly what we will discuss in our next lesson, and we will revisit the concept of union, intersection, difference, the concept of course, universal set and null set, and etc. And that's the point where you should be able to see what is exactly happening when we are doing set theoretic operations. Okay, so see you in the next lesson. Thank you so much.